integration by parts is going to be another technique for evaluating integrals that is going to be used with specific types of functions. So previously we already introduced integration by substitution. So integration by substitution was used whenever we were trying to integrate functions that were composite functions. So there was some inner and outer function. Integration by parts is going to be used when we try to integrate the product of two functions. So one of the main things to keep in mind with these two integration techniques, substitution and integration by parts, is when we should use each method. There's going to be some other similarities between the two methods, so it's going to be important to keep them straight, understand which approach we're using and why. So looking at each of these integrals below, we can see that in this case, for instance, we have the product of two functions, x, so we could let f of x equal x and g of x equal the natural log of x, which means what we're integrating in this case is the integral of f of x times g of x dx, or with respect to x. So when we look at these problems, we need to identify that we have the product of two functions and what those two functions are. So when we integrate x e to the x, our function f of x would be x, and g of x would be e to the x. And then we run into kind of an interesting case when we try to integrate the natural log of x. The natural log of x is a function all on its own, so f of x equals the natural log of x, and then we don't have any other functions left in the problem to be our g of x function. Unless we use a little bit of a trick and know that we can always multiply anything by 1 without changing that problem. So the trick for integrating a natural log function is to know that it's being multiplied by 1, so our function g of x is just the constant function 1. So when we look at these problems, we need to recognize that we have the product of two functions, and then we'll look at applying integration by parts. So the integration for parts formula, or the process, is constructed by looking at the original problem, selecting one of those functions to be u, and one part of that integral to be the statement dv. So we'll set part of the integral equal to u, part of it equal to dv. One of the tricks for integration by parts is knowing which part of your integral should be u. There's an acronym that can help with that, which is LIATE. So this applies more for math majors. There are actually some functions in here that we won't ever have to use, so math science majors have to use more of these. But for our purposes, if we're trying to select u, the first thing we would want to select is a log function. So if there's a log function like natural log, our u is going to be equal to that natural log function. I stands for inverse trig functions. We don't have to worry about that. A is for algebraic expressions. So if we have a power function or a polynomial, we'll let u equal that algebraic expression. And then our very last choice for u is an exponential expression. So something like e to the x. So our very first choice for u is a natural log function or a log function if that occurs. If there's some algebraic function, that becomes our second choice. Very last choice would be e to the x. So once we have u, then we'll find du, and to find du, we'll find du dx, what that's equal to. So u is going to be substituted for some expression. We'll take the derivative of both sides of that. Once we have our statement, our expression for dv, we'll find our value for v, and we'll get that by integrating dv, or if we want to, we can think of that as integrating 1 dv. So that'll give us our value for v. And then we'll take those different pieces and we'll write a new expression of the form u times v minus the integral of v du. So explaining this approach doesn't really make a lot of sense at first. We're kind of talking about these arbitrary substitutions. But when we get into the examples, we'll see this pattern start to take shape. Making the selections for u and dv, differentiating our u substitution statement, integrating our dv substitution statement, and then building some expression of this form.